Hi, this is the pre-video for the second lab of the Summer Haskell class. And the reason I'm doing this is because there's a lot of code, as you can see, 752 lines of code to run what is Lisp that is implemented in Haskell. So with 750 lines of Haskell code, you can create a better language than Java. It's a pretty bare bones list, but let's look at it. And my recommendation, so if you don't know how to run the labs, you just want to do a git clone of the Summer Haskell class repository. And the directory's here. And there is a lisp.hs, and then there's a Lisp directory that has all of its dependencies. So let's do cabal run. I'm actually going to useledit, which is a tool that makes command line interfaces easier. Like, you don't have to worry about that occurrence where you hit the back or the delete button and some weird character pops up. Withledit, it just makes it a lot easier to use. So we open up Lisp, and let me just make this a little larger. Let's talk about it a little bit. So if you're not familiar with Lisp, it uses Polish notation, also known as S expressions. So for example, to do this computation, that's going to be 165, because 5 plus 6, that's what that means, it's prefix notation, is 11, plus 7, 8, that's 15, and then you're multiplying them together, and you get 165. This particular Lisp only has one type of number. Like I said, it's very bare bones. It's more to prove a point, which is that you can have really as much dynamism as you want in Haskell. You just have to decide in advance what the dynamism is. And that's not always such a bad thing. Obviously, you're going to want to do more than just use this as a calculator. In this particular Lisp, many functions have arbitrary arity. So as you can see, I added, plus takes as many arguments as it gets and it sums them, including 0. That's fine too. And same with times. Now, you can define symbols. This is a scheme-inspired Lisp, but I'm using def. Oh, and that #t is true. So that's actually scheme-inspired, that aspect of it. Now we have a value of 5 in t, and we can use it like so. And for the rest of the session, it'll remember that. We have defen, add, multiply, x, y, z, plus x times y, z. And this should be 10,005. Okay, so what are some other features of this language? We have comparisons. And you've got the ability to define your own functions. You have branching. Let me talk about the 7, what I call the 7 dirty words, or the 7 fundamental operations of a Lisp. You have car and cdr, which operate on lists. So let's first make a list. That's not applying 1 as a function, because that wouldn't make any sense. That's a list with 1, 2, 3, 4 in it. The quote mark tells the REPL to, I don't want to evaluate this form. I want this list itself. And you can do that with symbols as well. If you do just a bare plus, then it says, oh, you're talking about the function. But if you quote it, it says, oh, you're talking about the symbol. That's another type that exists in this language. So car takes the first element of a list. It's like head, and it's an error if if it's an empty list, or if you try to apply it to something that's not a list. Footer is tail. So these are the roots of many of these functions that you see in Haskell. The whole concept of the linked list as the fundamental data structure comes from the Lisp heritage, which is now 55 years old. Cons is how you build up lists. You take an argument. My wife is presenting a cat to me. Hi, Henny. My cat did that. Cons puts something onto a list and puts the head onto it. Eq is symbol equality. In fact, the original definition of Lisp did not have numbers as a necessity, although in this system I've included them because they're too useful to ignore. Atom, which returns true if you give it an atom or the empty list, because in many Lisps they use the atom nil to represent the empty list. Oh, that's interesting. The REPL does not accept comments. That would be a bug worth fixing if you are looking to get your feet wet in this language. So there's that. What else? Atom, eq, cons, could, or car. Obviously, you need branching. That's going to return 56 because it goes in the false branch. Alternatively, some people will use, will say that cond is fundamental. Cond takes a list of lists of alternatives, a list of pairs where the left is the alternative and is the test, and then on the right side is what happens. So this is going to return B because 5 equals 6 is going to return false, and then equal 5 is going to return true. And if none of them check, then it returns a false, saying I didn't find anything. What else? Cond. Oh, and finally there's quote. Now, quote is the same thing as putting the quote before it. In fact, a quote around any form says to the evaluator, I don't want you to evaluate this, I just want to return this list. So those are the 7 dirty words, and we've got the numeric operators. And so we also have built-in, and I'll show you where these are defined. We have some of the neater features, like we have, lambdas. You should know about lambdas. They're, in this case, you give a lambda, you give the parameters, and you give the return. So in this case, we're mapping a function that adds 1 over the list 1, 2, 3. Get back 2, 3, 4. So let's some of the code. As I've said before, if you're looking for an entry point in an executable, the place to look is main. So prelude is, if you say no prelude, then you don't import the prelude.lisp function, if that's one of your arguments. Otherwise, you do run the prelude. And so main is going to execute a Lisp action. Run Lisp says execute a Lisp action with an environment that is either init-env, which is extremely bare bones, doesn't have anything defined except the built-ins. With prelude runs a Lisp file before it does anything. And then, there's some wrapping that you have to unwrap, like REPL is forever doing something, which is REPL1. That's one REPL iteration. Catching error with handle error. I'll go over these in detail in the class. I just want to sort of walk you through the code so that there's a basic understanding of what's going on. And then try REPL is going to read the input, and if it can parse it, if it can't parse it, it throws an error. If it can parse it, it calls a val, which is in, as you might expect, evaluator, which depends on Lisp.types. That's an important file to look at because everything depends on the types. The types are the language of the program. So eval takes a Lisp value and returns a Lisp of Lisp value. The question is, what is Lisp? And the answer is, it's a monad. The reason I went over monad transformers in lecture 7 is because I actually use them here. This is a wrapped around I/O, so it can do I/O, but it also has a state, which is a Lisp environment, which is defined also in this file. And then there's an except t because it can also fail. And it's actually very important that I have except t wrapped around the state t, because that gives me the ability to update the state even if there is an error. So if eventually I wanted my Lisp-env, which right now doesn't have it, but if I wanted it to have a count of how many errors occurred, I could do it. What else? Lenses are worth learning a little bit about because I use them here. I'll give a lecture probably dedicated entirely to lenses, but you'll see, anytime you see these 4 names, stack, globals, gensim counter, macros, without a preceding underscore, I'm referring to the lens, not the record field. A lens is built off of a record field, but it gives you the ability to set in a functional way in addition to getting. So that's that. Now let's talk about the why people find Lisp interesting. Because right now all I've shown is a stripped down language that, yeah, it's kind of cool, but I haven't really gotten into what makes it special. We have a val, which takes a form and executes it. So the evaluator is a function, not a pure function, obviously. It goes through the Lisp monad, in fact, that can take a Lisp form. So you can actually use Lisp to build up things that get evaluated. Eval list if list equals 5, 6, list times 10, 11, list 5, 1, 2. And that's going to evaluate that form as it builds it up. We also have a thing. So I mentioned defn. Now it's time to look at some code in Prelude. So, and rest is how I implement variarity. So if you want a function what should we do? If you want a function that takes multiple arguments, negative infinity. See if this actually works. Kind of doing it on the fly. This does not work because why? Interesting. So my minus operator is not doing the right thing because it should, when it has one argument, be negating it, and it doesn't. So let's try that. And it seems to work. And of course, the max of the empty list is negative infinity. So that's using and rest. That's just basically saying match this to a list of the remaining arguments. And you'll see that a lot because Lisp is very big into variarity. Now we define our defin, which we define as a function. Here's where Lisp kind of is different from Haskell. Well, there are many ways. But one of the major ones is that you couldn't write if it wasn't given to you if as a function. Because, for example, if you did defin myIf C T E, those are the condition in the else branches. And let's just make this true. And so that will print out barf. It will evaluate the side effects of that, even though they aren't used because of the false expression. If we throw an error in there, then the function fails, even though if is smart enough to say, I don't execute that. And that's because Lisp functions evaluate the argument, evaluate everything to a value before passing it into a function. So if and quote have to be special forms. And so that means that sometimes when you want to work with code, raw code without evaluating it, you need some tricks. For example, short-circuiting add is another, or and is another thing where we'd really like not to execute. We want short-circuiting. So and, as you might guess, is not implemented as a function. It's implemented as a macro. And the whole prelude's here. It's in the file. But we define defin as a function first, and then we set macro to it. And you're never going to use set macro once you have def macro. But what def macro gives you the ability to do is to define patterns that the compiler, there's sort of a mini compiler here, will recognize and be smart enough to expand without evaluating. So let's say that we want to create our own parallel language in which we reverse a form before we evaluate it. And in this particular version, any parameter that's prefixed with and will match the remainder of the list. So we define this macro that reverses the form before evaluation, and then we pass in 1, 2, 3 list, and it's going to first reverse it. No, it's not, because I didn't define reverse. So let's do that. This function really should exist. Otherwise, I don't care if this is slow. Not call that thing list. I'm actually going to use the function list. List now. I need to actually do footer. Let's see if this works. Wait a second. Oh. There we go. So now let's try it. And what it will do, you can look at this using macro expand, where you pass in the form and you see how it macro expands. It says that macro expands to list 321. There's macro expand 1 does 1 level of macro expansion. That may not always be enough. For example, sometimes you want a full macro expansion, sometimes you don't. So let's talk about or. Or does a let. It uses a generated symbol or a gensim, which is something that the language hasn't seen yet or shouldn't have seen yet, just to avoid colliding with things, just to avoid scope collisions with things that might exist. It lets that symbol equal the first thing, and then it says if that, as soon as it gets something that's truthy, it returns it. And I should mention that everything but false is truthy in this particular list. And if not, then it will go to or BC. Now let is also macro, so if you want to get all the macros expanded, then you use macro expand, and it expands the let form to this thing that's creating an anonymous function and applying a to it. And that's equivalent to letting G18 be a, where G18 is this anonymous gensim. And finally, if you want to get all the macros out of your code and just see a macro-free piece of code, which is something I had to do to debug this macro system, a hell of a lot of work. And in fact, the bug that took a week of work wasn't even in the macro system. You can use macro expand all, and you get the whole form. And that's not exactly readable or debuggable, so sometimes you just want to do a macro expand 1 to see if your macro works. So the core essence of Lisp, dynamic typing, first-class values, which Haskell, or first-class functions, which Haskell also shares, macros, macro expansion, all of that's in this 500-ish lines of code. The final thing I'll show is quit. And if you are inclined to run this without the prelude, you separate it with a double hyphen to say that you're passing in the no prelude option. And you don't have a prelude. So you only have the built-ins. And then if you want to load the prelude, or maybe you want to load some other prelude, load file prelude Lisp, and there you go. And now you have it. So have fun. Look at the code, about 700 lines of it, and let me know if you have any questions. All right, I'm going to sign off, and I'll see you in August. Bye.